Welcome to the Explainer. Today, we're going to crack open a really cool statistical tool, one that helps us find predictable patterns in events that seem, well, totally random.
Okay, so what do these things have in common? It sounds like a brain teaser, right? But the answer is actually this super fascinating statistical concept that lets us find a hidden order in all sorts of random happenings.
So here's how we're going to tackle this. We'll kick things off with what a Poisson distribution even is. Then we'll get into the rules of the game, and after that, we'll dive into some really cool case studies. We're talking hurricanes and the lottery. Finally, we'll wrap up with why all this stuff actually matters.
All right, first up, what is a Poisson distribution? Let's get right to the heart of it and find some order in all this randomness.
So the official definition talks about a discrete probability distribution for events over an interval. But what does that really mean? Well, simply put, we're counting how many times something happens within a specific set boundary. Think about it. We're not measuring, say, how strong a hurricane is, but how many of them occur in a year. It's all about frequency.
And what's really cool is how flexible this idea of an interval is. It doesn't just have to be time, like calls to a help center per hour. It could be distance, like counting potholes per mile of road, or even area, like weeds in a square meter of your garden. It can even be volume, like bacteria in a liter of water. It's super versatile.
Okay, but we can't just start using this for everything. There are some rules to the game. 4 key requirements, actually. You have to make sure your situation checks these boxes before you can dive in.
So here they are. First, you have to be able to count the occurrences. Easy enough. Second, they have to be random. No predictable patterns allowed. Third, they need to be independent. One event happening doesn't make another one more or less likely. And finally, they should be spread out pretty evenly over whatever interval you're looking at. If you can tick all 4 of these boxes, then, my friend, you can unleash the power of the Poisson formula and make some seriously amazing predictions.
And this is the magic formula. Now, I know, it looks a little scary with all those symbols. You got your mu, your x, your e, but don't worry, it's actually way simpler than it looks. The whole thing really just revolves around one key piece of information, that little Greek letter mu, or mu. And mu is just a fancy way of saying the mean or the average number of times something happens.
All right, enough with the theory, right? Let's put this thing to the test. We're going to look at a pretty powerful real-world example, Atlantic hurricanes.
We're going to follow a simple 3-step plan. First, we'll find the average. Then, we'll calculate the probability of a specific number of hurricanes. And finally, we'll see how our prediction stacks up against reality.
Okay, step 1, find the mean. We've got data from over 118 years. And in that time, there were 652 Atlantic hurricanes. So you just divide 652 by 118, and what do you get? You get 5.5. So our mean, our mu, is 5.5 hurricanes per year. Now for the fun part. We take that mean, 5.5, and we plug it right into our formula. We're going to test for the probability of having exactly 6 hurricanes in any given year. So in our formula, x equals 6. After you run the numbers, the formula spits out about 0.157. So what does that mean? It means our model is predicting there's a 15.7% chance of having exactly 6 hurricanes in any random year. Not too high, not too low.
And here is where it gets really cool. This is the model versus reality. Our formula predicted a 15.7% chance. So over 118 years, you'd expect to see about 18.5 years with 6 hurricanes. And what actually happened? In reality, there were 16 years with 6 hurricanes. I mean, how close is that? 18.5 predicted, 16 in reality. That's pretty incredible. It tells us this model is actually really good at describing this kind of thing.
Okay, so we've seen that it works, it's a solid model, but now let's look at a really clever trick that statisticians use. Turns out, the Poisson distribution can be a powerful approximation, a kind of statistical shortcut. Here's the secret sauce. You can use Poisson as a shortcut for something called the binomial distribution, which can be kind of clunky to calculate. But you can only do it if 2 magic conditions are met. First, you need a lot of trials. We're talking 100 or more. And second, the probability of success on any single trial has to be really small. If you've got those 2 things, you're golden. So how do you use the shortcut? Well, you just need to calculate the mean, your mu, in a slightly different way. You just multiply n, that's your number of trials, by p, the probability of success. Super simple. So let's use this powerful shortcut to answer a question that, let's be honest, we've all probably wondered about at some point. Can we beat the system? What are the odds of actually winning the lottery?
Okay, here's the problem we're going to solve. We're looking at the main Pick 4 lottery, and let's say you're committed. You play once every single day for a whole year. That's 365 days, 365 trials. The probability of winning on any given day? A tiny, tiny 1 in 10,000.
So let's check our magic conditions. Is our number of trials, n, greater than or equal to 100? Well, n is 365, so yep, check. Now, is n times p less than or equal to 10? Let's see, 365 times 1 in 10,000 is 0.0365. That is way less than 10, so check again. This is a perfect candidate for our Poisson shortcut. Now, here's our strategy. Trying to calculate the probability of winning once or twice or 3 times, that would be a huge pain. So we're going to use a classic statistician's trick. We'll calculate the probability of the opposite happening. We're going to figure out the odds of winning 0 times, and then we just subtract that from 1.
So we use our Poisson formula with our new mean, which was 0.0365, and we're solving for x equals 0. 0 wins. The answer comes out to 96.42%. Ouch. That means after playing every single day for a year, there's a more than 96% chance you'll have won absolutely nothing.
So if the chance of winning nothing is 96.42%, what's the chance of winning at least once? Well, it's just 1 minus that number, which gives us 3.58%. So there you have it. Your odds of winning at least one time all year are just under 4%. And the Poisson shortcut got us there super fast and with amazing accuracy. Okay, let's bring it all home. Why does any of this matter? What are the key takeaways here?
So here's what you should really take away from all this. First, the Poisson distribution is this amazing tool for modeling the probability of random, independent events happening in a fixed space or time. Second, it has a ton of real-world applications, everything from predicting natural disasters to spotting defects in manufacturing. And third, it's a super handy shortcut for calculating odds in situations where you have a lot of tries, but a very low chance of success, like the lottery. It really is a powerful way to find order in a world that often feels random.
Think of it like a new lens for seeing the world. Now that you can spot these hidden patterns in random events, what are you going to look for next? Once you start searching, you'll be amazed at what you find.